In the vast darkness of space, approximately 3,000 light-years from Earth, something extraordinary lurks in the constellation Sagittarius. The Red Spider Nebula, catalogued as NGC 6537, represents one of the most violent and mysterious phenomena observable in our galaxy. This isn't just another beautiful cosmic object to admire through telescopes. This is a stellar death chamber, a place where a dying star is tearing itself apart in one of the most energetic displays the universe has to offer. When we look at images of NGC 6537, we see what appears to be a cosmic arachnid frozen in space, its legs extending outward in perfect symmetry. But this resemblance to a spider is merely our human tendency to find patterns in chaos. What we're actually witnessing is matter being expelled from a dying star at velocities that challenge our understanding of stellar physics. We're talking about winds moving at speeds exceeding 1,000 kilometers per second. To put this in perspective, that's roughly 3,600,000 kilometers per hour. At such speeds, you could travel from Earth to the Moon in less than 8 minutes. The central star of this nebula is what astronomers classify as a white dwarf, but calling it simply a white dwarf doesn't capture the extreme nature of this object. This stellar remnant has one of the hottest surfaces ever measured, with temperatures reaching an almost incomprehensible 250,000 degrees Celsius. Our Sun, by comparison, has a surface temperature of merely 5,500 degrees. This white dwarf is nearly 50 times hotter. The amount of energy being radiated from this tiny stellar corpse is staggering, and it's this intense radiation that creates the spectacular visual display we observe. The structure of the Red Spider Nebula tells us a story that spans thousands of years. When we examine the nebula's architecture, we see distinct layers and waves of material, each representing a different episode in the star's death throes. The star didn't simply explode or quietly fade away. Instead, it underwent a series of violent outbursts, each one ejecting massive amounts of stellar material into space. These ejection events weren't random. They followed patterns dictated by the star's rotation, its magnetic field, and possibly the influence of an unseen companion star. The waves and arcs we observe in the nebula's structure are shock fronts, places where fast-moving stellar winds collide with previously ejected material. When these collisions occur, the kinetic energy is converted into heat and light, causing the gas to glow with characteristic colors. The red hue that gives this nebula its name comes primarily from nitrogen atoms that have been stripped of electrons by the intense ultraviolet radiation from the central star. When these ionized nitrogen atoms recapture electrons, they emit light at specific wavelengths that appear red to our eyes. But there's more to the color story. Hidden within the Red Spider Nebula are regions glowing in other colors invisible to human eyes. Ultraviolet and X-ray emissions reveal even more violent processes occurring. The Hubble Space Telescope, using its various instruments, has captured NGC 6537 in multiple wavelengths, and each view reveals new layers of complexity. In ultraviolet light, we see the hottest regions, where atoms are being completely ionized. In infrared, we detect dust particles and cooler molecular gas. Each wavelength tells a different part of the story. The central white dwarf itself is a physics laboratory unlike any we could create on Earth. In this tiny object, roughly the size of Earth but containing more mass than our Sun, matter exists in a state of extreme density. A single teaspoon of white dwarf material would weigh several tons on Earth. The atoms are packed so tightly that electrons are torn from their parent nuclei, creating what physicists call degenerate matter. In this state, normal atomic structure breaks down, and quantum mechanical effects become dominant. Understanding how NGC 6537 formed requires us to trace back the history of its progenitor star. Several million years ago, this star was probably similar to our Sun, perhaps slightly more massive. For most of its life, it burned hydrogen in its core, maintaining a stable equilibrium between the inward pull of gravity and the outward push of radiation pressure. But when the hydrogen fuel in the core was exhausted, this equilibrium was broken. The core began to contract and heat up, while the outer layers expanded dramatically. The star entered what astronomers call the red giant phase. During this red giant phase, the star swelled to enormous proportions, possibly large enough to engulf the orbits of inner planets if any existed. The surface temperature dropped, giving the star a reddish appearance, but the total energy output increased dramatically. Deep in the core, helium began to fuse into carbon and oxygen. This helium-burning phase was relatively brief on cosmic timescales, perhaps lasting only a few million years. When the helium was exhausted, the star faced another crisis. Without fusion to support it, the core collapsed further, becoming denser and hotter. But for a star of this mass, the temperature never became high enough to fuse carbon. The core became a white dwarf, supported not by fusion but by electron degeneracy pressure. Meanwhile, the outer layers of the star became increasingly unstable. Thermal pulses, sudden bursts of fusion in shells around the core, caused the star to dramatically brighten and eject material into space. These pulses occurred repeatedly, each one stripping away more of the star's outer envelope. The ejected material didn't move away uniformly in all directions. Instead, it was shaped by several factors. The star's rotation created a disk of denser material around the equator. Magnetic fields, channeling charged particles, created jets along the rotation axis. If a companion star was present, its gravitational influence would have further distorted the outflow. The result is the complex, bipolar structure we observe today. The speed at which material is being ejected from NGC 6537 is what truly sets it apart from other planetary nebulae. Typical planetary nebulae have expansion velocities of 20 to 30 km per second. The Red Spider Nebula's winds exceed 1,000 km per second, making it one of the fastest known. This has led astronomers to classify it as a particular type of object, a planetary nebula with a very hot central star and unusually fast stellar winds. What drives these extreme winds? The answer lies in the radiation pressure from the central star. With a surface temperature of 250,000 degrees, this white dwarf is emitting enormous amounts of ultraviolet radiation. Photons carry momentum, and when billions upon billions of photons strike atoms and molecules in the surrounding gas, they transfer that momentum, accelerating the gas to incredible speeds. But there's more to the story. The star may have recently undergone a very late thermal pulse, a final burst of fusion that temporarily reignited nuclear burning and dramatically increased the star's luminosity. The geometry of NGC 6537 reveals clues about the physical processes at work. The nebula exhibits clear bipolar symmetry, with two lobes extending in opposite directions from the central star. This is common in planetary nebulae and indicates that the mass loss was concentrated along the star's rotation axis. Between these lobes is a denser equatorial region, often called the torus or waist. This structure suggests that the progenitor star was rotating, and that rotation influenced how material was ejected. Within the bipolar lobes, we can see intricate filamentary structures. These filaments are regions where the density or composition of the gas differs from its surroundings. Some filaments mark the edges of shock fronts, where fast wind collides with slower moving material. Others may trace magnetic field lines, along which charged particles flow. Still others could be dense clumps that survived the initial ejection and are now being ablated by the stellar wind. The chemistry of the Red Spider Nebula is particularly interesting. When stars evolve through the red giant phase, they dredge up material from deep in their interiors. Material that has been processed by nuclear fusion. This means the ejected gas is enriched in elements heavier than hydrogen and helium. We find enhanced abundances of nitrogen, carbon, and oxygen, the products of fusion in stellar cores. These elements will eventually be incorporated into new stars and planets, making planetary nebulae like NGC 6537 crucial to the chemical evolution of galaxies. Spectroscopy, the analysis of light split into its component wavelengths, provides detailed information about the nebula's composition, temperature, and velocity. Each chemical element produces a unique set of spectral lines, like a fingerprint. By identifying these lines, astronomers can determine what elements are present. The width and shape of the lines reveal the temperature and motion of the gas. Doppler shifts tell us whether material is moving toward or away from us. Through careful spectroscopic analysis, astronomers have mapped the three-dimensional structure and kinematics of NGC 6537. One particularly intriguing aspect of this nebula is the presence of what appear to be jet-like structures. These narrow, collimated outflows extend from the central region along the nebula's axis. Jets are common in young stellar objects and in active galactic nuclei, but their presence in planetary nebulae is less well understood. They may be produced by the interaction between the stellar wind and a strong magnetic field, which channels the outflow into narrow beams. Alternatively, they could result from focused bursts of mass ejection during thermal pulses. The age of the Red Spider Nebula can be estimated from its size and expansion velocity. If material is moving at 1,000 km per second and the nebula extends about half a light-year from the central star, simple mathematics tells us the nebula is roughly 500 years old. However, this is a simplification. The expansion velocity may have changed over time, and different parts of the nebula may be expanding at different rates. More sophisticated modeling suggests the nebula could be anywhere from a few hundred to a few thousand years old. In cosmic terms, NGC 6537 is extremely young. Most planetary nebulae are thousands to tens of thousands of years old. The youthfulness of the Red Spider Nebula means we're observing it during a particularly dynamic phase. The intense stellar wind is still actively shaping the nebula, and the structures we see today will look very different in a few thousand years. This makes NGC 6537 an excellent laboratory for studying the physics of stellar winds and nebular evolution. The distance to NGC 6537 is not precisely known, which introduces some uncertainty into our understanding of its physical properties. Different measurement methods yield distances ranging from about 1,000 to 5,000 light-years. The most reliable estimates place it around 3,000 light-years away. This distance uncertainty affects our calculation of the nebula's actual size, the luminosity of the central star, and the total mass of ejected material. Even with this uncertainty, it's clear that NGC 6537 is a substantial object, containing at least a tenth of a solar mass of gas and dust. Dust plays an important role in planetary nebulae, though it's less visually obvious than the glowing gas. Dust grains form when elements like carbon, oxygen, and silicon combine in the cooling gas. These tiny particles, typically less than a micron in size, absorb ultraviolet and visible light from the star and re-emit it in the infrared. Infrared observations of NGC 6537 reveal the presence and distribution of this dust. The dust traces the history of mass loss, with different generations of dust grains formed during different ejection episodes. The central star of NGC 6537 is evolving rapidly. As the remaining nuclear fuel is exhausted and the star continues to contract, it will eventually cool and fade, becoming a cold, dark black dwarf. But this process takes billions of years. Currently, the star is still extremely hot and luminous, pumping enormous amounts of energy into the surrounding nebula. Over the next few thousand years, the star will gradually cool. And as it does, its emission will shift to longer wavelengths. Eventually, the ultraviolet flux that ionizes the nebular gas will decrease, and the nebula will begin to fade from view. As the star cools, the nebula will continue to expand. The expansion will carry the material farther from the star, and the density will decrease. At some point, the nebula will merge with the interstellar medium, becoming indistinguishable from the general background of gas and dust between the stars. The elements forged in the star's interior and dispersed by the nebular ejection will be incorporated into future generations of stars. In this way, planetary nebulae like NGC 6537 are part of the great cosmic cycle of stellar birth, evolution, death, and rebirth. Observations of the Red Spider Nebula have been conducted using many of the world's most powerful telescopes. The Hubble Space Telescope has provided the most detailed visible light images, revealing structures as small as a few hundred astronomical units. Ground-based telescopes equipped with adaptive optics systems have also captured impressive views. Radio telescopes have mapped the distribution of molecular gas, while X-ray observatories have searched for emission from the extremely hot central star and from shocked gas. Each new observation adds to our understanding, but also raises new questions. Why is the wind from the central star so fast compared to other planetary nebulae? What role does magnetic field play in shaping the nebula? Is there an undetected companion star influencing the system's evolution? These questions drive ongoing research, and NGC 6537 remains an active area of study for astronomers. The question of a companion star is particularly intriguing. Many, perhaps most, stars form in binary or multiple systems. If the progenitor of NGC 6537 had a companion, that companion could have profoundly influenced the system's evolution. As the primary star expanded into a red giant, the companion could have orbited within the giant's extended envelope, a situation astronomers call a common envelope phase. Friction in the envelope would cause the companion to spiral inward, transferring energy to the envelope and helping to eject it. This process can explain the bipolar morphology and the high mass loss rates observed in some planetary nebulae. If a companion exists in NGC 6537, it hasn't been directly detected. This doesn't rule out its existence, as the companion could be a relatively small, faint object overwhelmed by the light of the hot white dwarf. Future observations, particularly with next-generation telescopes, may reveal a companion or definitively rule one out. The presence or absence of a companion has significant implications for our understanding of the nebula's formation and evolution. The Red Spider Nebula also serves as a preview of our own Sun's distant future. In approximately 5 billion years, our Sun will exhaust its core hydrogen and begin evolving into a red giant. It will swell to perhaps 100 times its current size, possibly engulfing Mercury and Venus. The Earth, if it survives, will be scorched and lifeless. Eventually, the Sun will eject its outer layers, creating a planetary nebula not unlike NGC 6537, though probably less dramatic. The Sun's core will become a white dwarf, slowly cooling over trillions of years. This fate awaits all stars similar to our Sun, those with masses between about half a solar mass and 8 solar masses. More massive stars end their lives in supernova explosions, while less massive stars become white dwarfs without creating planetary nebulae. The range of stellar masses that produce planetary nebulae encompasses a significant fraction of all stars, making these objects common in galaxies. The Milky Way contains tens of thousands of planetary nebulae at various stages of evolution. Planetary nebulae were historically misnamed by early astronomers who, using small telescopes, thought these objects resembled planets. The name stuck even after it became clear these objects had nothing to do with planets. Today, astronomers understand that planetary nebulae represent a crucial phase in stellar evolution, the brief period between the end of fusion burning and the final white dwarf stage. This phase lasts only a few tens of thousands of years, a blink of an eye in cosmic terms, but during this time the star returns much of its mass to the interstellar medium. The material ejected in planetary nebulae is enriched with heavy elements, elements essential for life as we know it. The carbon in our bodies, the oxygen we breathe, the nitrogen in our DNA, all were forged in the interiors of stars and distributed through space by processes like those we observe in NGC 6537. When we study planetary nebulae, we're studying the origin of the elements that make up our world and ourselves. We are, quite literally, made of star stuff, and planetary nebulae are part of the mechanism that made us possible. The symmetry of NGC 6537 raises interesting questions about the physical processes that shape planetary nebulae. Perfect symmetry is rare in nature, yet many planetary nebulae show remarkably symmetrical structures. This suggests that the shaping mechanisms are robust and repeatable. The most widely accepted model involves the interaction between a fast stellar wind from the central star and a slower, denser wind from the earlier red giant phase. The fast wind carves out cavities in the slower wind, creating the bipolar lobes we observe. But this generalized model doesn't explain all the details we see in NGC 6537. The extremely high wind speeds, the intricate filamentary structures, the jet-like features, all require additional physics beyond the simple interacting winds model. Magnetic fields almost certainly play a role, channeling ionized gas and creating structures aligned with field lines. Rotation of the progenitor star influences the shape of the density distribution, creating an equatorial concentration of material. Instabilities in the wind can produce clumps and filaments. The full picture is complex, involving magnetohydrodynamics, radiation transfer, atomic physics, and thermodynamics. Computer simulations have become essential tools for understanding planetary nebulae. By encoding the relevant physics in computer code and running simulations on powerful supercomputers, researchers can model the evolution of these objects from the start of mass loss through the fully developed nebula phase. These simulations can reproduce many of the observed features of real nebulae, validating our understanding of the physics involved. They also allow us to explore scenarios that would be impossible to test observationally, such as varying the mass of the progenitor star or the strength of the magnetic field. Simulations of objects like NGC 6537 are particularly challenging because of the extreme conditions involved. The wind speeds are supersonic and even hypersonic, requiring special numerical techniques to handle the shock waves that form. The radiation from the central star must be treated carefully, as it drives much of the system's evolution. The computational domain must be large enough to encompass the entire nebula, yet resolved finely enough to capture small-scale structures. Despite these challenges, modern simulations have achieved impressive agreement with observations. The study of NGC 6537 also connects to broader questions in astrophysics. Understanding stellar winds helps us comprehend mass loss from stars throughout the universe, from newly formed stars to dying giants. The shock physics relevant to planetary nebulae also applies to supernova remnants, active galactic nuclei, and even the large-scale structure of galaxy clusters. The atomic physics of photoionization and recombination, crucial for interpreting nebular spectra, is the same physics at work in the atmospheres of exoplanets and the interstellar medium. By studying specific objects like the Red Spider Nebula in detail, we develop tools and insights applicable across astronomy. One of the most visually striking aspects of NGC 6537 is the contrast between the bright, colorful nebula and the dark background of space. This contrast reminds us that space is not truly empty. Between the stars exists the interstellar medium, a tenuous mixture of gas and dust with an average density of about 1 atom per cubic centimeter. This may seem like a vacuum by terrestrial standards. And it is, but over the vast distances of space, the interstellar medium contains substantial mass. The material ejected by NGC 6537 will eventually merge with this medium, slightly enriching it with heavy elements. The interstellar medium is not uniform. It contains regions of varying density and temperature, from cold molecular clouds where stars form to hot, tenuous regions heated by supernova explosions and stellar winds. Planetary nebulae like NGC 6537 inject energy and material into the interstellar medium, helping to maintain its complex structure. The kinetic energy of the fast stellar wind creates shocks and heats the surrounding gas. The ultraviolet radiation from the central star ionizes nearby regions. Over time, these effects propagate outward, influencing an ever larger volume of space. The Red Spider Nebula is invisible to the naked eye from Earth, too faint and too small for unaided human vision. Even with modest amateur telescopes, it appears as nothing more than a faint, fuzzy spot. Only with large professional telescopes or long-exposure imaging does its intricate structure become apparent. This is true of most celestial objects. The universe is filled with wonders invisible to our eyes, revealed only through technology and the patient work of astronomers. The name Red Spider Nebula itself is part of a tradition in astronomy of assigning evocative names to celestial objects. Other planetary nebulae bear names like the cat's eye, the butterfly, the helix, and the ring. These names help make these distant objects more relatable, turning abstract catalog numbers into objects with character and personality. They also reflect our human tendency to find familiar shapes in random patterns, a cognitive trait called pareidolia. The universe doesn't care what we call these objects, but the names help us remember and communicate about them. NGC 6537 was first catalogued in the New General Catalogue, a compilation of astronomical objects published in the late 19th century. The NGC remains one of the most widely used catalogues in astronomy, despite being well over a century old. Many objects have been re-observed countless times since their original cataloging, with each new generation of telescopes revealing new details. NGC 6537 has benefited from this progressive improvement in observational capabilities, and undoubtedly future telescopes will reveal even more about its structure and evolution. The upcoming generation of extremely large telescopes, with mirrors 30 to 40 meters in diameter, will be able to study NGC 6537 in unprecedented detail. They will resolve structures currently too small to see, measure velocities and compositions with greater precision, and perhaps detect a companion star if one exists. Space-based telescopes operating in wavelengths absorbed by Earth's atmosphere will provide complementary views. Together, these facilities will push our understanding of planetary nebulae to new levels. But there's a philosophical dimension to studying objects like NGC 6537 as well. When we observe this nebula, we're looking at light that left it thousands of years ago, traveling through space at the universe's speed limit. The nebula we see is not as it is now, but as it was in the past. In fact, there is no meaningful now for distant objects in a relativistic universe. What we observe is always the past, and the farther we look, the farther back in time we see. NGC 6537, 3,000 light-years away, appears to us as it was 3,000 years ago, around the time of ancient Egypt and the late Bronze Age on Earth. This time delay means that the nebula has continued evolving during the millennia its light has been traveling to us. The structures we observe have expanded, changed, evolved. If we could somehow teleport to NGC 6537 instantly and view it as it exists in our present reference frame, it would look different from the image we see through our telescopes. This is part of the challenge and fascination of astronomy. We must infer the present from observations of the past, using our understanding of physics to model how objects evolve. The Red Spider Nebula reminds us of the dynamic nature of the universe. The cosmos is not static and unchanging, but evolving at every scale. Stars are born, live, and die. Galaxies merge and interact. The universe itself expands, carrying galaxies away from each other. Change is the only constant. NGC 6537 captures one moment in this great cosmic dance, a star in its death throes creating beauty from destruction. There's also something poignant about planetary nebulae. They represent stellar death, the end of billions of years of stable existence. Yet they're beautiful, with their intricate structures and vivid colors. They're creative, forging and dispersing elements essential for life. They're temporary, fading in a few tens of thousands of years. In their brief existence, they embody themes that resonate with human experience: the transformation of death into new beginnings, beauty arising from chaos, the impermanence of all things. The question of visiting NGC 6537 in person takes us from the realm of observational astronomy into the domain of speculation and perhaps future possibility. What would it mean to actually travel to the Red Spider Nebula, to float in space among those glowing filaments and witness the death of a star firsthand? The journey would be staggering in both distance and danger, yet imagining it helps us appreciate the true nature of this cosmic phenomenon. At 3,000 light-years distance, NGC 6537 is utterly unreachable with current technology. Our fastest spacecraft, the Parker Solar Probe, travels at about 190 kilometers per second at its maximum speed. At that velocity, it would take approximately 5 million years to reach the Red Spider Nebula. Human civilization itself is younger than that. The pyramids of Egypt were built only about 4,500 years ago. 5 million years is an almost incomprehensible span of time for creatures who live mere decades. Even if we could somehow achieve speeds approaching the speed of light, the journey would present extraordinary challenges. At such velocities, even individual atoms of interstellar hydrogen become deadly projectiles, their kinetic energy sufficient to destroy any known material. Cosmic rays, high-energy particles racing through space, would pose a constant radiation threat. The ship would need shielding beyond anything we can currently manufacture. Life support systems would need to function flawlessly for the entire journey, with no possibility of resupply or repair from Earth. But let's imagine, for a moment, that these technical obstacles could be overcome. Let's suppose that some far future civilization develops the technology to reach NGC 6537. What would they find upon arrival? The first surprise would be the sheer emptiness of the nebula. Despite its vivid appearance in photographs, the Red Spider Nebula is almost a perfect vacuum by terrestrial standards. The glowing gas has a density far lower than any vacuum we can create in laboratories on Earth. If you could somehow float unprotected in the middle of the nebula, you wouldn't see the vibrant reds and intricate structures visible in telescopic images. Those colors exist only because of long-exposure photography and the way telescopes gather light from vast volumes of space. To the human eye, the nebula would appear faint, ghostly, perhaps barely visible at all against the background stars. The gas is simply too tenuous to glow brightly from any single vantage point. You would need to be surrounded by cubic light-years of this material, gathering photons from all directions, to see what telescopes show us. The beauty of NGC 6537 is a cumulative effect, the sum of countless faint emissions across immense distances. The central white dwarf would dominate the view. This tiny star, roughly the size of Earth but blazing with the intensity of 10,000 suns, would be the brightest object in the sky by far. Its light would be intensely blue-white, shifted toward ultraviolet wavelengths that human eyes cannot see, but that would be deadly to unprotected human tissue. The ultraviolet radiation from the star would be so intense that it would ionize any gas in its vicinity, stripping electrons from atoms and creating a harsh radiation environment utterly incompatible with organic life. Approaching the central star would be suicidal without extraordinary protection. The temperature of 250,000 degrees isn't the temperature of the space around the star, it's the temperature of the star's surface. But the radiation from that surface would heat anything that came near. The stellar wind, particles streaming away from the star at 1,000 kilometers per second, would buffet any spacecraft with a force far beyond anything experienced in our solar system. These particles carry immense kinetic energy, and their impact would erode any material surface, ablating it atom by atom. The structure of the nebula would become apparent only when viewing it from a distance. From within, the filaments and arcs would be difficult to perceive. They would appear as slight variations in brightness and color across the sky, subtle gradations that might not form a coherent picture. You would need to move through the nebula, changing your vantage point, to appreciate its three-dimensional architecture. What appears as a two-dimensional image in our telescopes is actually a complex three-dimensional structure, with material at different distances from the central star and moving at different velocities. The sound of the Red Spider Nebula is something we never consider because sound cannot travel through the vacuum of space. There is no air to carry pressure waves, no medium for vibrations to propagate. The nebula would be utterly silent. The violent collisions between fast and slow winds, the shock fronts heating gas to millions of degrees, the ionization and recombination of atoms, all these energetic processes would occur in complete silence. It's a strange thought, that one of the most violent events in the galaxy proceeds without a sound. Yet if we could somehow convert the electromagnetic radiation into sound, or detect the plasma waves that do propagate through the ionized gas, perhaps we would hear something. Radio telescopes detect emissions from celestial objects by receiving electromagnetic waves, which can be converted into sound waves for human ears. These sounds are not the actual sounds the objects make, but translations of their electromagnetic signatures into audible frequencies. The Red Spider Nebula might hum with a deep, throbbing tone corresponding to the rotation of the central star, or crackle with high-frequency noise from turbulent plasma motions. The passage of time near NGC 6537 would proceed normally, unaffected by the exotic physics at work in the nebula. Unlike near a black hole, where extreme gravity distorts spacetime and causes time dilation, the Red Spider Nebula is not sufficiently massive or compact to produce relativistic effects. A clock carried to the nebula would tick at essentially the same rate as a clock on Earth, accounting only for the slight time dilation due to motion if the spacecraft were traveling at high velocity. The astronauts would age normally, experiencing time in the familiar way. But there would be a profound psychological effect to witnessing such a spectacle. Humans have gazed at the stars for all of recorded history, wondering about their nature, their distance, their meaning. To actually travel to one of these distant objects, to see it up close, would be transformative. The realization of the true scale of space, the insignificance of Earth in the cosmic scheme, the ephemeral nature of stellar life, all would become viscerally real in a way that no amount of studying images and data can convey. The question arises whether such a journey would have scientific value. Couldn't we learn everything we need to know about NGC 6537 through remote observation? To some extent, yes. Modern astronomy has become remarkably good at extracting information from light. Spectroscopy tells us about composition and temperature. Photometry reveals brightness and variability. Astrometry tracks motion and changes in position. Interferometry achieves resolution beyond what single telescopes can provide. The James Webb Space Telescope and other advanced instruments gather data across the electromagnetic spectrum, from radio waves to gamma rays. Yet there's always the possibility that in situ measurements would reveal something unexpected. Instruments placed within the nebula could measure the plasma density, temperature, and magnetic field with precision impossible from afar. They could collect samples of the gas and dust, analyzing isotopic ratios and molecular compositions directly. They could monitor changes on timescales of days or weeks, detecting fluctuations too rapid to catch with telescopes 3,000 light-years away. They could search for phenomena we don't even know to look for, discoveries awaiting serendipitous detection. The dust grains within NGC 6537 would be of particular interest. These microscopic particles, forged in the cooling gas ejected from the dying star, contain information about stellar nucleosynthesis and grain formation processes. Collecting these grains would be like capturing time capsules from the star's interior, physical samples of material processed by nuclear fusion. Analysis of these grains in a laboratory, using techniques like mass spectrometry and electron microscopy, could reveal details about the star's history and the conditions in which the grains formed. But perhaps the most valuable reason to visit NGC 6537 would be simply because we could, because the journey itself would represent an achievement of human or post-human capability. Exploration has always been part of our nature. We crossed oceans, climbed mountains, ventured into space, not always because there was immediate practical value, but because we wondered what was there. We explored because we were curious, because we wanted to test our limits, because we sought to expand the boundaries of the known world. A journey to the Red Spider Nebula would be exploration in its purest form. Such a journey would require not just technological advancement but a fundamental shift in how we think about time and space. It would require civilization to take a long view, to invest in projects whose completion lies centuries or millennia in the future. It would require a species united in common purpose, able to cooperate across generations to achieve a goal that none of the initiators would live to see. Perhaps this is the real barrier to visiting NGC 6537, not the technology but the social and political will to undertake such an endeavor. Or perhaps the answer lies not in physical travel but in virtual presence. Advanced telescopes and instruments could serve as our eyes and hands in distant locations, gathering data and transmitting it back to Earth. Artificial intelligence could process this data, creating virtual reality simulations indistinguishable from being there. We could explore NGC 6537 in immersive detail without ever leaving Earth. This might seem like a lesser achievement than actual travel, but it could provide most of the scientific benefit at a fraction of the cost and risk. The Red Spider Nebula will not wait for us. It continues its evolution, indifferent to human observation or aspiration. Over the coming millennia, the nebula will expand and fade. The central white dwarf will cool. Eventually, tens of thousands of years from now, the nebula will merge with the interstellar medium and disappear. Future civilizations, if they arise, will not see NGC 6537 as we see it today. They will find only a faint white dwarf cooling in space, with perhaps some subtle trace of the surrounding dispersed material detectable only with the most sensitive instruments. This impermanence adds urgency to our study of NGC 6537 and objects like it. We live in a brief window of time during which this particular nebula is visible and spectacular. It won't last forever. In the grand timeline of the universe, planetary nebulae are fleeting phenomena, existing for mere moments before fading away. We're privileged to observe them during their brief display. The story of NGC 6537 is ultimately a story about change and transformation. It's about a star that exhausted its fuel and transformed into something entirely different, ejecting its outer layers and revealing its core. It's about matter returned to space, enriched with heavy elements, ready to participate in new cycles of star and planet formation. It's about energy being redistributed, kinetic and radiative, heating the interstellar medium and influencing its structure. Nothing in the universe is permanent. Everything changes, transforms, evolves. For humanity, NGC 6537 serves as both a teacher and a mirror. It teaches us about stellar evolution, about the physics of ionized gases, about the cycle of matter in the cosmos. It mirrors our own existence, reminding us that all things have a beginning and an end, that beauty can arise from endings, that what seems like death can be a transformation into something new. The elements that will someday form new planets, perhaps even new life, are being forged and distributed right now in nebulae like this one scattered throughout the galaxy. When we look at images of the Red Spider Nebula, we're seeing across both space and time. We're seeing an object 3,000 light-years distant as it appeared 3,000 years ago. We're seeing a process that began long before recorded human history and will continue long after our current civilization has passed. We're seeing the universe engaged in one of its fundamental activities, recycling stellar material, mixing and redistributing elements, preparing the ingredients for future generations of cosmic structure. The mathematically precise nature of the physics governing NGC 6537 is remarkable. The equations of radiation transfer, fluid dynamics, thermodynamics, and atomic physics that describe this nebula are the same equations that apply everywhere in the universe. The laws of nature are universal, and an object 3,000 light-years away obeys the same rules as a laboratory experiment on Earth. This universality is one of the great discoveries of modern science. It means we can understand distant objects, can model their behavior, can make predictions about their evolution, all from our small vantage point in space. Yet for all our understanding, mysteries remain. We still don't fully understand what makes some planetary nebulae symmetric and others irregular. We don't know for certain what role magnetic fields play, or how important companion stars are to shaping nebular morphology. We can't yet predict with certainty what the Red Spider Nebula will look like 10,000 years from now. Our models are sophisticated but incomplete. Each new observation brings answers but also new questions. This is the nature of science. It's not a fixed body of knowledge but an ongoing process of discovery, a conversation between theory and observation. We propose models to explain what we see, then test those models against new data. When the models fail, we revise them. When they succeed, we extend them to new domains. The study of NGC 6537 contributes to this process, providing tests of our theories and opportunities for discovery. In the end, the Red Spider Nebula is significant not because it's unique but because it's one example of a universal process. Stars are dying throughout the universe, creating planetary nebulae in galaxies near and far. Each one is slightly different, shaped by the particular circumstances of the progenitor star, but all follow the same basic pattern. By studying NGC 6537 in detail, we learn about planetary nebulae in general. By understanding planetary nebulae, we understand stellar evolution. By understanding stellar evolution, we understand galaxies, cosmic chemical evolution, and ultimately our own origins. We are connected to NGC 6537 by bonds of matter and physics. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were created in stars and distributed through space in events like the one we observe in this nebula. We are literally made from stellar debris, assembled from atoms forged in stellar furnaces and scattered by stellar winds and supernovae. When we study the Red Spider Nebula, we're studying our own deep past, the processes that created the raw materials from which Earth and life were eventually constructed. This perspective can be humbling or exhilarating, depending on how you view it. We are small, temporary creatures on a small planet orbiting an ordinary star in an ordinary galaxy. Yet we have the capacity to understand our place in the cosmos, to trace our origins back through billions of years of cosmic evolution, to comprehend the physics of dying stars 3,000 light-years away. We may be small, but our minds are not. Our understanding reaches across the universe. The Red Spider Nebula NGC 6537 will continue its expansion and evolution whether we observe it or not. It doesn't need our attention. But we need it, and objects like it, to satisfy our curiosity about the universe and our place within it. We study it because we wonder, because we question, because we seek to understand. These impulses are as fundamental to human nature as anything else. They've driven us to explore our world and reach for the stars. They'll continue to drive us as we push further into space and deeper into time, seeking always to know more about the universe we inhabit. So we return to our telescopes, our instruments, our calculations. We observe NGC 6537 across the electromagnetic spectrum. We model its evolution with supercomputers. We write papers and share discoveries. We teach new generations of astronomers who will carry the work forward. The Red Spider Nebula shines in the constellation Sagittarius, a beacon of stellar death and transformation, and we watch, we learn, and we wonder what other secrets the universe has yet to reveal.